Hi everyone. Today let's talk about section 7.4, partial fractions. So we will learn the technique partial fractions decomposition that is used for evaluating the integral of a rational functions. That is the ratio of two polynomials. Do you remember that at the beginning of this semester we said for integrals there's no product rule, no quotient rule? Even though we don't have product rule, but when we see some products, we might able to use integration by parts, but it's only for certain types of products. And even though we don't have quotient rules, but we have this technique called partial fraction, it can also help us to solve the integral of certain types of quotients, but not all, okay? Big skills. You should be able to decompose various types of rational functions into simple, proper fractions that can be easily integrated using the known formulas. So first, consider rational functions. So f of x equals p of x over q of x, where p and q are polynomials. It is possible to express f as a sum of simple fractions, provided the degree of the numerator is less than the degree of the denominator. Such rational functions is called proper. So proper means the degree of the numerator is less than the degree of the denominator. Okay, so if it's improper, we can use long division to get the remainder such that degree of the remainder is less than the degree of the denominator. Okay, so this is long division, and you can see now s of x, this is polynomial. And we know how to integrate polynomial. And then the remainder over the divisor, this guy is a proper fraction. Okay, so given a rational function, step 1, you want to see whether that is proper. Okay, if it's proper, then you can go to the step 2. And if it's not proper, use long division. Okay, so if not, use long division. So far, so good? Okay, so step 2. Step 2, look at the denominators. Okay, so look at the denominators. And we want to factor the denominator completely. So, factor denominator completely. Okay, and then depending on the types of factors, we can separate into 4 cases. The first case, when we have distinct linear factors. So, i.e., what's distinct linear factors? Linear factor is like ax plus b. So, we have all the distinct linear factors multiplied together. This is for the denominator, okay? So, if we see this, then we can form the partial fraction decomposition by writing, so we can split all the linear factors and we add them, and because we can decompose into simple proper fractions. Simple means you can see for each of the term, the denominator only consists one kind of factor. It's not a product of 2 factors, okay? So this is simple. And proper means you see the degree of the numerator is still less than the degree of the denominator. And when we set it up, we want to set up the general form. So that's why, because the degree of the denominator is 1, then the degree of the numerator, in order to be proper, the degree of the numerator must be 0. And that means we have a constant term. Okay? So we decompose into simple proper fraction. And then next, we can multiply both sides by the common denominator, and this will produce conditions for all the constants ai's, and then we can solve it. Okay? And we will do a lot of examples, okay, after we discuss the different of cases. And the second cases is when we have repeated linear factors. So you can see this R1 and Rn, they are the multiplicities. Oops, let me write better. Multiplicity. Multiplicity is the number of copies of that factor. Okay, so in this case, instead of a single term of a1 over a1x plus b1, then we start with one copy in the denominator, and then we increase two copies until we reach the multiplicity. Okay, and the numerator is always the constant term if we have a degree 1, okay, linear factor. So this is a setup when we have a repeated linear factor. You start with one copy in the denominator, and then you increase the power until you reach the multiplicity, but the numerator is always constant. Okay, because we want to have a proper factor. Okay, so next, case 3, irreducible quadratic factor. So what is irreducible quadratic? Well, irreducible quadratic means the quadratic factor cannot be decomposed into a product of two linear factors. And what does that mean? Do you remember the quadratic quadratic function is the polynomial, right? So we have okay, this case, and this case. Well, the first case, we have two real roots, right? This means that we can decompose the quadratic factor in terms of a factor of two linear factors. In this case, the discriminant b squared minus 4ac, which is the things inside the square root, is positive. So we have two real roots. Well, the middle one, so we have a repeated real root, i.e. the discriminant b squared minus 4ac equals 0. Okay, so we have a repeated real root. Last, we have no real roots, so that means we have two complex roots. And then the discriminant is actually negative in that case, because then you will see square root of minus 1, which is I. Okay, so if we have irreducible quadratic, then it means the discriminant b squared minus 4ac is less than 0. And then how do we set it up? Well, our denominator is degree 2 because we want to set up with the proper fraction. So the degree of the numerator must be less than 2. So degree is 1. The general form for degree 1 function is ax plus b. Okay, so you can see when we break down, the degree of the numerator is always less than the degree of the denominator. This is the third case. Okay, so whenever you see a quadratic factor, you should check the discriminant. If it's negative, then it's irreducible. If it's positive, then you can go ahead and factor into a product of two linear factors. Okay, case 4, repeated irreducible quadratic. And then suppose we have the multiplicity r, and then instead of setup of one term, you start with one copy in the denominator, and you increase the copy until you reach the multiplicity. And all the numerator are linear functions, okay? Because the degree of the numerator must be less than the degree of the denominator. Okay, so those are the 4 cases. Now, let's do some example. Example 1. Complete factors, functions classify each factor is linear or irreducible quadratic, and states its multiplicity. Okay, so first example, let's factor it. Can you see a common factor? X squared, right? So we can factor out x squared, and then we have 81 x to the 4 minus 16. Okay, do you realize 81 is like 9 squared, and x to the 4 is like x squared squared? So I realized this looks like a squared minus b squared. And how do you factor it? Well, that's a plus b times a minus b. So in this case, we have 9x squared plus 4 squared is 16, right? So a plus b and a minus b. And this guy is an irreducible quadratic. But this guy, we can factor further. How? Well, this is x squared, 9x squared plus 4, and I can factor as 3x plus 2 and 3x minus 2. So far, so good, everybody. Okay, now let's look at each factor. So, let me use a different color because I don't have much space here. Okay, so you can see x. Well, x is a linear factor. But you might say, isn't it x squared? Isn't it a quadratic factor? It's a linear factor with multiplicity 2. Okay, it's still a linear factor. The 2 is the number of the copy. So it will be a multiplicity 2, but still linear factor. 9x squared plus 4 is irreducible quadratic. And with multiplicity 1. And then 3x plus 2 and 3x minus 2, they are both linear factors with multiplicity 1. So far, so good, everybody. Okay, let's look at the next example. Okay, next example. If you see 3 terms, like quadratic factor, you try to factor it. But if you see 4 terms, what do you usually do? You group the first 2 terms together, and you group the last 2 terms together, and you try to factor the common factor. Here you can see the common factor is x cubed, right? And then 2x plus 3. And here the common factor is 8, and then we have 2x plus 3. Now you can see 2x plus 3 is a common factor. And then we have x cubed plus 8. Can we factor x cubed plus 8? By the way, in this session, you must be able to factor all the you can factor until you reach either the linear factors or quadratic factor. So if you see a degree 3 factor, well, then you must be able to factor further, okay? Until you reach either linear factor or irreducible quadratic factor. Okay, so what is x cubed plus 8? Well, I'm gonna remind you the formula. So x cubed plus 8 cubed, what is this? Well, that's x plus a, and then x squared. So if this guy is plus, then the middle term is gonna be minus xa plus a squared. Okay, if this guy is minus, flip the sign here, and then this becomes plus. And how do I remember the second term? The second term looks like the complete square, but you don't have the 2 in the middle. Right? What is complete square? A plus b squared is like a squared plus 2ab plus b squared. So complete square, you have the 2 in the middle, but you right now you just have no 2. Okay, and the sign is opposite with the sign in front of it. This is how I remember it. Okay, so that's why this is 2x plus 3, and then x plus 2, x squared minus 2 times x. Okay, so 2 times x plus 2 squared, which is 4. Okay, so now, and this guy is always, so if you use this formula, this guy is always irreducible quadratic. So this is irreducible quadratic. Okay, so that's why we can write down our answer. So 2x plus 3 is linear factor with multiplicity 1. X plus 2 is linear factor with multiplicity 1, and x squared plus minus 2x plus 4 is irreducible quadratic with multiplicity 1. So far, so good, everybody. Okay, so this is how we factor the denominator. Okay, next, write down the general form of the partial fractions decomposition of H. You're not required to solve for the constants in the numerator. Okay, first of all, we want to check whether is this fraction proper or not. let's look at part A. What is the degree of the numerator? 5, right? How about the degree of the denominator? Well, you see, this is square, but square and cubit, this is like 6. And this is square and square, so 2 times 2, 4. So the degree of the denominator is actually 10. Okay? So, this guy is proper. Okay? So, degree of numerator is 5. Degree of denominator is 10. Why 10? 2 times 3 plus 2 times 2. Okay, so this guy is proper. So remember, if it's improper, then you need to use long division. Okay, now how do we set it up? So first of all, we need to check have we factored the denominator completely? Okay, how do we check? Let's see. Let me move this down a little bit. Okay. So how do we check this? Well, look at this discriminant. B squared minus 4ac. Okay, b squared minus 4ac. B squared is 81 minus 4ac. Oops. So you can see this is actually positive, so we can factor further. So let's see, the numerator stay the same. And so don't factor the numerator, we just factor the denominator. Okay, how can we factor it? Well, 2x, x, right? We can do plus 5 and minus 1. That will give us plus 9 in the middle. And then each factor cube it, right? And next, this guy, discriminant b squared, oh, there's no b. Minus 4 times 11c is 4. So this guy is negative. We know it's irreducible quadratic. So we can just copy it down. So this is how we factor it completely. And then, what's next? Well, look at this case. Look at the first factor. This is case 2, right? Repeated linear. So for repeated linear, how do we set it up? Well, we have 1 copy and then 2 copy until you reach the multiplicity. Okay, so far so good. And how about the constants? How about the numerators? They're constants, right? So we can do A, B, C. All right. Next, well, this guy is also case 2, a repeated linear, right? We start with that factor and we increase the number of copy until we reach the multiplicity. And the numerator is also constant, right? Okay, A, B, C, D, E, F. Okay, you might want to sing an ABC song to when you write the constants, okay? But make sure you don't have the same one, okay? You don't repeat the constants. The next one is case 4. It's repeated. Irreducible quadratic. So we start with 1 copy plus we increased the multiplicity. Increase the power until we reach the multiplicity. Okay, so and then remember the numerator are linear functions. So we should have x term and we should have constant term. So A, B, C, D, E, F, G, H, I, J. Okay, so here we have a lot of constants. So in the exam, there are two types of questions that I will ask you. This is one kind. I ask you to set up the general form and you might expect to see many constants. Okay, and you don't need to solve the constants. And the second type is I actually ask you to solve the integral. Okay, in this case, you should have at most 4 constants. Okay, so yeah, when you have a lot of constants, you don't need to solve the constants. Just set up the general form. Okay? Alright, let's continue and look at part B. So is it proper? What's the degree of the numerator? So degree of the numerator is 6. Degree of the denominator is 2. Also 2 times 2 plus 2 times 3, which is 10. So this guy is also proper. So far, so good, everybody. Okay, let's move that a little bit. Okay, so let's look at this guy. Okay, so now you can see the discriminant b squared is 4 minus 4ac 3 and 5. Oh, this is negative, so we know this is irreducible quadratic. And the second one, discriminant is b squared minus 4ac, but it becomes 4 times 25 times 16, because minus become positive, so this is positive, so we can factor the second quadratic factor. So let's see. And you can see in this process, during the setup, we don't change the numerator. Actually, the numerator does not matter. It won't affect the setup, okay? But it will affect the constants. After we set it up and we solve the constants, the numerator will affect the constants, the values of the constants. Okay, the first factor is irreducible quadratic. Just keep it here. And the second factor, okay, you can see, we can actually factor it. This is like a squared minus b squared. So it's 5x, a plus b, so plus 4 and 5x minus 4, and each of them cube it. Oh, then this example is very similar to the example we have in the previous example, right? So we have 3x squared minus 2x plus 5. This is case 4, right? This is case 4. So and then you increase the copy, right? And then this guy is case 2. This is case 2. So you have that factor, and then you increase the power until you reach the multiplicity. And also we have 5x minus 4 and 5x minus 4 square, 5x minus 4 cube. Okay, so you can write out all the denominator. Now you're gonna write down the numerator, then we can sing the ABC song. The first factor is gonna be linear, so A, B, C, D, and all the remaining are linear factors, so the numerator is gonna be constant. So A, B, C, D, E, F, G, H, I, J. Okay, so this is how we set it up. Of course, the order doesn't matter. You can write this guy first and then write this guy at last. The naming of the constant might change, but the number of the constants is still the same. So far, so good, everybody. Okay, next. Okay, it's time to actually solve the integral. Okay, so let's look at the first problem. First 4. Is this proper? The degree of the numerator is 2. The degree of numerator is 2. Degree of the denominator is 3. Is this proper? Yeah, it's proper. And then next, have we factored the denominator completely? Yes, it's already a product of 3 linear factors, so it's already factored completely. Then we can look at the types of the factors, right? So we write down, so we're not integrating yet. We write down the rational function, And we're gonna do the partial fraction decomposition because all of those are linear factors, so we are in case 1. So we have x minus 1 and x plus 1 and x plus 3. And our setup is just constant on top of the linear factors. So this is our setup. So far, so good, everybody? Okay, next, we want to solve the A, B, C. How do we do it? We multiply by the common denominator. And this is the common denominator, right? So next steps, we want to multiply by the x minus 1, x plus 1, x plus 3. Okay, then the left-hand side is just the numerator because the denominator just cancel out. Okay, how about the right-hand side? Okay, see? This guy multiplied by this, and this guy. You can see this guy cancel. So we have A times x plus 1 times x plus 3. The second term, x minus 1, x plus 1, x plus 3. X plus 1 cancel, so you have B, x minus 1, x plus 3. And then x minus 1, x plus 1, x plus 3, and then you cancel out. We have C times x minus 1, x plus 1. So far, so good, everybody? Okay, so here there are 2 ways to solve the constants. So the 2 ways to solve the constants. The first way is to, because this equation is true for all x. So the first way is we pick some x values, okay, and then we plug in, and then we get systems of linear equations, okay, to solve the constants A, B, C. Okay, so here we have 3 unknowns, A, B, C, right? So we need 3 equations to solve 3 unknowns. So we pick 3 x values to plug in, and then we can get 3 equations and solve the unknowns. This is the first way. The second way is we multiply everything out. Okay, oops. So multiply everything out, and then we compare the like terms. Okay, so you compare the constants, and you compare the linear terms, and you compare the x squared terms. The coefficient of them must be agreed. Then you also get 3 equations to solve 3 unknowns. Okay, so if a problem has a lot of linear factors, it's better to use the first method, the first way, okay, to plug in some x values. Okay, so this one, good. This one is good when we have many linear factors. Okay, so for example, here, what are the values we want to plug in? Okay, so what values you want to plug in? You usually plug in the values, the x values, such that it makes the linear term 0. Okay, so let's look at this linear term, x plus 1. So what x can make this guy 0? Well, you pick x equals minus 1. Now what happened? Well, we plug in x equals minus 1. This one, minus 1 squared is 1. And then 4 times minus 1 minus 4 plus 1. This is the left-hand side. But the right-hand side, what happened? Well, x plus 1, when you plug in, is 0. And then the b, okay, x minus 1, so minus 1 minus 1 is minus 2. Minus 1 plus 3 is 2. But the c, can you see the c has the factor x plus 1? And then this guy is also 0. So as long as the terms consist of the factor x plus 1, it's gone. And now you can see here, what do? We get negative 2 equals b times negative 2 and 2. So negative 2 cancel, b equals 1/2. You see, we can solve b easily. right? So that's why this method is very useful, especially when your denominator consists a lot of linear factors. So you just choose the x values which make the linear factor 0. Okay, what is the next value we should plug in? Well, look at this guy. What x can make this guy 0? Well, x equals 1, right? So plug in x equals 1. And then on the left, 1 plus 4 plus 1. On the right, 1 plus 1 is 2. 1 plus 3 is 4. But the b has the factor x minus 1, so this guy is 0, and the c has the factor x plus 1. This guy is also 0. Ooh, so you can see 6 equals a times 8. So a is 6 over 8. The common factor is 2, so 3 over 4 is our a. Isn't it very nice? Okay, how about next one? What values shall we plug in? Well, we look at this factor. What values can make this factor 0? Well, we plug in -3, right? -3 squared is 9. 4 times -3 is -12. And then the first factor has a -3, x plus 3, so it's 0. B is also multiplied by 0. And C, -3 minus 1 is -4. -3 plus 1 is -2. Okay, on the left, we have 10 minus 12, -2. And on the right, we have C times -4 times -2. -2 cancel. So C is -1/4. See, we can solve A, B, C easily just putting in the x values of which make the linear factor 0. Okay, so here, caution, everybody, be careful. Let me use this color. So we plug in the values here. Don't plug in here. Why? Because some students just plug in the value there. Well, then you get the denominator is 0, and then the student gets stuck. So I do have previous students. You must multiply and clear the denominator, then you can plug in the values. Don't plug in the values when you still have the denominator, because then you just have 0 in the denominator, so it's undefined. So don't do that. Okay, I hope you don't make this mistake. Okay. All right. So let's continue. We have A and B and C. Okay, finally. Our integral, okay, I don't want to copy everything. So integral is, we can decompose. A is 3 over 4 over x minus 1. Okay. Plus B is 1/2. X plus 1. C is -1/4 x plus 3 dx, right? And we can separate them. So we can put a constant in front. So we have this guy and this guy and -1/4. Okay, so far so good. All right, so here you can see this is we can do something like use substitution in our head. So that's why here the first one you can think of u is x minus 1 and du is just dx. So then we have 3 over 4 integral of du over u is ln of absolute value of u. So this is absolute value of my u is x minus 1. Okay, and the second one, the u is gonna be x plus 1, so we still have du is dx. So integral of that is ln of absolute value of u, but my u now is x plus 1. And then the last one, we have ln of my u is x plus 3. But you guys gotta be very, very careful. It looks like, when we have the linear term in the denominator, and then the integral is gonna be ln of the denominator. Well, some errors might pop up. Okay, so let me show you. Be careful. Okay, so be careful. Okay. Let's say if you have integral of dx of 2x plus 5. Okay, so your u is 2x plus 5. So when you find your du is 2 dx. So that's why when you want to match a du there, you want to multiply by 2. And when you multiply by 2, you also need to divide by 2. That's why this is 1/2. And then you have integral of du over u. This is ln of absolute value of u. See? When you have, for example, if the coefficient of x is not 1, you actually have some things in front of the ln. So it's not always simply just ln of the linear factor. Okay, you might have some coefficients in front because your du might not be dx. So far, so good? Okay, let me highlight the 1/2. Okay, so be careful. So far, so good, everybody? Okay, so let's continue and work on more examples. Okay, so let's look at this example. Okay, first of all, is this a proper fraction? Oops. The degree of the numerator is 3. The degree of the denominator is 2. This is improper. Well, when we have improper fractions, what do? Make it proper, so use long division. This is 2x cubed minus 4x squared minus x minus 3. And this is x squared minus 2x minus 3. Okay, do you still remember long division? So what's multiplied by x squared to get 2x cubed? 2x, right? So 2x times x squared is 2x cubed. 2x times 2x is 4x squared. 2x times negative 3 is minus 6x. And then we use the first line, subtract the second line. So negative x minus negative become positive. Minus x plus 6x is 5x. And negative 3 minus 0 is negative 3. Oh, now can you see? So we decompose. The integral is, this is the quotient plus the remainder over the divisor. So far, so good. And so this guy, we know integral of 2x is just x squared. But you can see now the second integral is a proper fraction, right? So we can use the partial fractions decomposition methods. We can we factor the denominator? That is x minus 3 and x plus 1, right, everybody? Okay, so both of them are linear factors. So 5x minus 3, x minus 3, x plus 1. So both of them are linear factors. So this is how we set it up. And we put A and B here. Alright, so what is the next step? We multiply by the common denominator to clear the common denominator, right? So to clear all the denominator. So the first thing, okay, A, because you multiply by x minus 3 and x plus 1, x minus 3 cancel. So we have just x plus 1. And the B we multiply by x minus 3 and x plus 1. X plus 1 cancel, so we have x minus 3. So far, so good, everybody? Okay, next, because we have, remember, we have two ways to solve the constants, but because here we have a lot of linear factors, it's better to pick x values. So, what x values shall we pick? X equals minus 1, right? Then we have minus 5 minus 3 equals, when we plug in minus 1, the first term is gone. Then we have b times minus 1 minus 3 minus 4. Oh, that's minus 8 equals b times minus 4. So b is 2. So far, so good, everybody. Next, we plug in x equals 3. 5 times 3 is 15. And, 3 plus 1 is 4. And you can see the second term, 3 minus 3 is 0, so it's gone. So, yeah, the picking x values method is very useful when we have a lot of linear vectors, because after you plug in those values, you see only one constant is left. Then you can just solve the constants. Okay, so here, we have 12 equals 4a, then a is 12 over 4, which is 3. Okay, so finally this guy equals, the integral equals, I just put this symbol because I want to say this guy is what I want to continue to write. Okay, so this guy equals x squared and then plus, okay, so the integral is a is 3. And we can also separate them, right? And b is 2. So actually, we can move the a and b in front. Right? Okay, next, we can do the u substitution in our brain. This here, u is x minus 3, du is dx, so integral of du over u is ln of absolute value of u. So it says here, u is x plus 1, du is dx. Integral of du over u is ln of absolute value of u, but my u is x plus 1. And yeah, and here, because du is just dx, so it's simply ln of the absolute value of the linear factor. But if the coefficient of x in the linear factor is not 1, then you might need to be careful. So look at this case. Okay. Alright. So far so good, everybody. Okay. Next, let's look at part C. So part C, we have integral of 6x plus 7 over x plus 3 squared. Okay, so you can see it's already factored completely, and the degree of the numerator is 1, degree of denominator is 2. So this is a proper fraction, right? And so we can go ahead and set it up, and you can see the denominator is a repeated linear factor, so we are in case 2. Okay, so when we are in case 2, how do we set it up? So we have 6x plus 7, x plus 3 squared. We set it up. We first have that linear factor plus 2 copy, of that linear factors, right? And the numerator is just constants. This is how we set it up. What is the next step? Well, we can multiply by the common denominator, which is x plus 3 squared. So we have 2x plus 7. Here we have a times x plus 3 plus b. So b times x plus 3 squared, it cancels, so we only left with the b. So far, so good. Next, we can pick x values. We only have one kind of linear factor, so it will give us x equals -3, right? When you plug in -3, you get -3 times 6, -18 plus 7 equals, well, you can see a times 0 is 0, and that is b. Oh, so b equals -11. So far, so good. Okay, what is the other x values? There's only one kind of linear factor, so we don't have a second type of linear factor. We can plug in that the x values correspond to that. And it's okay. You can plug in any x values. So actually, you don't need to. So this equation is true for all x. and you want to solve a and b, two unknowns, which means you need two equations. So you want to pick two x values to plug in, and you can plug in any number for x. It's not necessary plug in -3, but the good thing of when you plug in -3, what happened? Well, this guy, the a multiplied by 0, so x plus 3 is gone. So then you're only left with one constant. You can solve it easily. But if you plug in other values, so I will pick 0. 0 is easy, right? So then what happened when you plug in 0? Left hand side you get 7. The right hand side you get 3a plus b. So in general, if you plug in any x values, you should get a linear equation involving the constants a and b. So it's not only just one constant, it's usually that number of, so you have two constant unknowns, and then you should have the two unknowns. It's a linear equation with two unknowns. Okay, but here it's okay. We already get b is -11. We can plug in, so 7 equals 3a minus 11. We can move the -11 on the left, becomes 18. Oh, so a is 6. Okay, so you can also pick x equals 1 or 2 or -1. Any x values works. So you might just end up getting a system of linear equations, right? Do you know how to solve system of linear equation? For example, how do you solve like 2x plus 3y equals 7 and minus x minus 2y equals 10, something like this? How do you solve it? We can use elimination techniques, right? Okay, use elimination techniques or substitution techniques. So what is elimination techniques? We want to compare the coefficient of x and y. Which one is easier? Well, x is easier, right? Then you find the least common multiple, which is 2. So you multiply by the second equation by 2. Then you have minus 2x minus 4y equals 20. This is equation 3. Then you can add equation 1 and 3 together to get rid of the x. So 3y minus 4y is minus y. Oh, 7 plus 20 is 27. So you get your y is minus 27. Then you can plug in your equation 1 or equation 2 to solve for x. Plugging equation 2 is easier. So minus x minus 2y. 2 times that, okay, so negative become positive, and we have 54 equals 10. Well, then x equals 54 minus 10, which is 44. Okay. So far so good. So this is in general how to solve systems of linear equations. Okay. Next, so after we figure out a and b, by the way, this is let me use this. So this is, oops, okay. I want to say this is outside of our problem. Okay, so let's continue with our example. So we have integral a is 6, so we can move the 6 outside, and then we have dx over x plus 3. B is minus 11, and then we have dx over x plus 3. So here, how do we solve it? Well, here we use the u substitution. U is x plus 3, and du is dx. And then this is integral of du over u, which is just ln of absolute value of u. So we get this. But the second one, our u is also... Sorry, I forgot square. Our u is also x plus 3, and then the du is still dx. But then this guy is like integral of u to the negative 2 du. What's the integral of that? Is u to the minus 1 over minus 1 plus c. So u is x plus 3, u to the minus 1, it means it's in the denominator. And then the minus, we'll flip this sign, and we have plus c. So this is our answer. So far, so good. So if you're familiar with the U substitution in your brain, then you don't need to write out this. Okay, you can just think about those in your mind or your scratch paper, and then you can write down this. Because in this session, partial fraction, you in general you might see many terms like our part A. You see 3 terms. If you write out all the U, each terms your U is gonna be different things. So if you're familiar with the U substitution in your brain, then you can just write down based on the integral, write down the answer directly without writing down like what is U, okay, for each of the term. So far so good, everybody. Okay, so that is part C, and let's continue in the next video, part B. Okay, video part B. See you soon.